So simplifying the heat equation has been able to yield us the thermal circuit model. And we've been using the thermal circuit model to understand how the temperature of spatially complex objects changes over space. But we haven't been able to address the key question, which is, how do temperatures change over time? How does the heat equation prescribe what the temperature of an object is as a function of time? And in particular, can we simplify the heat equation enough that we'll be able to get an expression for what the temperature over time is, or at least an approximate expression for that, for some object without having to resort to understanding the complex mathematics of partial differential equations? Now, can we create a simple enough model that we can attack it with the tools of standard, boring old one-dimensional calculus and not have to rely on PDEs? The answer is yes. And the model that we're going to develop is called the lumped capacitance model. And to understand how we develop this, let's consider a very typical scenario in the study of, heat transfer, one which should be relatively intuitive. So imagine that we have some complex potato or rock or whatever. It has some weird shape, and it has a volume V and a surface area AS. And this thing is exposed to some fluid, it can be air or solid, which has some heat transfer coefficient H and some ambient temperature T infinity. I'm going to refer to it as T infinity. This potato has standard heat transfer properties. It has a specific heat capacity, it has a density, it has a thermal conductivity. And so we would like to try to figure out, well, what is the change of the temperature of this thing over time if we prescribe it to have some initial temperature T0 and then we dunk it or expose it to this liquid and then, let nature take its course. If we do such a scenario, we have to make one assumption in order to be able to get anything meaningful out of this. And that assumption is that the liquid, which we had identified before as being very large, right? That this liquid is so large that this temperature T infinity is not going to change regardless of how much energy this rock or potato, regardless of how much thermal energy this thing is either expelling or absorbing, to and from or from to the environment. Okay, so we're going to assume that this is just a very, very large liquid with constant temperature T infinity. And so the only thing that we want to track is the temperature of this solid object over time. And how do we do it? Well, there's already an issue, which is that if I tried to write down, what the temperature of this object is, we already know that the temperature of an object, of a solid object, isn't necessarily uniform. In fact, it can't be if heat transfer is happening inside of the object, because we had said the conductive heat fluxes, the heat fluxes that happen inside of an object are proportional to the thermal gradients in the object, okay? So we can't really just say that the temperature of this thing is just a single number, because then heat transfer doesn't happen. What we can do, however, is we can try to check to see under which conditions the temperature gradients or temperature differences inside of this potato are small enough that even though they will be real, right, there will be thermal gradients, that we can just kind of ignore them, that we can use a single temperature and then use that as kind of the representation of the temperature everywhere in this system. Under which conditions would that work? Well, we have to get a little technical with this. The first thing that we have to do is to try to create some kind of geometrically representative object that, no matter what the shape of this rock is, will have some kind of uniform geometric representation that we can then do analysis on, right? Because you can imagine that having a complex geometry would lead to all kinds of issues with the math, in particular from the perspective of trying to study heat transfer that's happening in more than one dimension. We want to try to see if we can't turn this into a geometrically representative one-dimensional system. And what we're going to do is we're going to say, well, what I want to do now is I want to create a sphere, okay? And this sphere is going to have a radius which is equal to LC. And that LC, which I'm going to call a characteristic length, right? Because it's, a characteristic length that is representative of the size of this object, which we'll see in a second. This characteristic length is just the volume of the original object divided by the surface area of the object over which the heat transfer is taking place. Okay? Which, for this potato, is just all of it. So we have a sphere. We're going to assume that heat transfer is happening one-dimensionally over this representative sphere, and we're going to assume that this LC, that the radius of the sphere is LC. Okay? But it's going to have the same material properties. All right? And it's exposed to a liquid with the same properties as well. So, how do we get an answer to this? Well, consider what would happen if I tried to do an energy balance right on the edge of this object. Okay, so here's what I mean. If I try to analyze heat transfer that's happening right at the edge of my sphere, the conductive heat flux at every point going into the edge has to be the same as the convective heat flux going outwards, right? Or, going inwards too. And so if that's the case, then we can say, well, minus K dt dr, right, has to be equal to H times T minus T infinity. Now you might be wondering, right, I skipped a couple of steps here. This is technically an energy balance. You might be wondering, well, if this system is changing over time, then why on earth do we not have like a temporal change term? And the reason that we don't have a temporal change term is because the region of space that we're considering is infinitely thin. And so even though thermal energy can flow in or out of it, it can't accumulate inside of it because there's no volume. This little sliver, this spherical sliver has no volume. And we've also divided by the surface area of the little sliver because it's the same on both sides because the thickness is arbitrarily small. Nevertheless, we wind up with this. But remember that we had said that the temperature of the object is not necessarily well defined. Like, what does that mean? And so because we don't know this, and because we have to assume some non-zero value for this or everything falls apart, what we can do is we can say that at the core of this sphere, we have some temperature Tc, and then at the surface, we have some temperature Ts. Okay? And we can approximate, and this is not a good approximation, right, that this characteristic length is small enough that dt dr can be approximated as Ts minus Tc divided by Lc. Okay, and so this is just a standard linearization. All that we're doing here is we're saying, well, the rate of change of the temperature with respect to R, this Lc is small enough that this is roughly constant and roughly equal to this. So if we do that, what expression are we going to be left with? Well, what we're going to be left with, and I'm going to absorb the minus, right? When I actually write down the expression for dTdr, there's a minus that shows up in the conductive expression, which I'm going to flip. And I'm just going to get that K Tc minus Ts divided by Lc is equal to H Ts minus T infinity. This is the expression that I'm left with. And this is very, very meaningful because if you think about it, right, what we want, the goal is to make this temperature difference small. We want the temperature difference of the core of the sphere, between the core of the sphere and the surface of the sphere to be small. If that temperature difference is small, then that means that it doesn't matter if we pick the temperature of the core or the temperature of the surface of the sphere as a representative temperature. Both of these things are going to be pretty close to each other. But we don't necessarily have a sense of scale. Like, if we find that this temperature difference is 10 degrees Celsius, is 10 degrees Celsius large, small? is 10 degrees Kelvin, large, small, 10 degrees Fahrenheit. We need some kind of comparative scale. And the comparative scale is being provided by this term right here. And so what we need to do now is not necessarily to check if this is small, but to check if the ratio of this and this is small. That's what will tell us whether or not the temperature differences inside of the object are negligible. And we can find, kind of surprisingly, that when we solve for that temperature difference, that what we get is something which is independent of the temperatures. We just get this dimensionless grouping of parameters, right? The heat transfer coefficient times the characteristic length divided by the thermal conductivity. And whenever this is small, that means that this is small, which means that we can assume a single temperature, Tc or Ts, to accurately represent the temperature of the entire object, at least based on our assumptions. And this little dimensionless grouping, and by the way, notice it's dimensionless, right? Because it's a ratio of temperature differences. So this doesn't have units and this doesn't have units either. This thing is commonly referred to as a Biot number. And so we say that when the Biot number is small, when this grouping of terms is small, that the temperature differences inside of a solid object are negligible. So how small does it have to be in order to make this assumption? There is no like hard and fast rule. Science can't tell us that because how small we want to make these ratios is entirely up to us. However, there is a kind of socially agreed upon, conclusion, at least for heat transfer people, which is that if the Biot number is smaller than 0.1, that is to say that this temperature difference is at least 10 times smaller than this temperature difference. Whenever that's true, then we can make the assumption that the temperature inside of this object is basically uniform. Okay? And so this is the criteria that heat transfer, engineers and physicists have agreed upon in order to determine whether or not we can actually assign a single temperature to an object. So supposing that this is true, so supposing that these conditions hold, now we actually have to try to create an expression. We have to try to create an equation. So how do we do it? Well, the first thing that we should try to do is to try to do an energy balance. And this time, we are not going to assume steady state because, after all, we are dealing with a system where temperatures change over time. So let's do an energy balance around the solid object, okay? And let's say, just like we did before, that the energy, the rate of change of the thermal energy of this object is equal to the rate of change, or pardon me, the rate at which energy flows in minus the rate at which energy flows out plus the rate at which energy is generated inside of our little system. What does that give us? Well, if we think about it, this term has to be equal to 0 because of the fact that, well, there's no thermal energy generation that's happening in the little ball. We can also, and this is going to be the key one, right? We can take a look at what the behavior of this term is. And we had said before that this rate of change was something that looked a little bit like this, right? So Cp rho times the volume times the temperature. It's the rate of change of the thermal energy of the whole thing over time. Now, if we assume that the specific heat capacity and the density and the volume don't change over time, then this simplifies considerably. We're also going to assume, by the way, that there's no changes in temperature, at least inside of the system over space, right? Which is what the whole Biot number being smaller than 0.1 is. And if we do that, then we can replace the partial derivative with a nice ordinary derivative, right? The rate of change of temperature over time. This has to be equal to the net amount of heat that is being transferred in or out of the system. So how do we determine if it's going in or out? We're just going to make an assumption about whether or not it's going in or out, and then write it down consistent with that assumption. Let's assume that because this has a uniform temperature, that the heat transfer, the heat fluxes everywhere on the boundary of this object are constant. And so the heat transfer rate, which we are assuming is entirely out, okay, is just the heat fluxes times the surface area. And those heat fluxes, because they're going into environment, are convective heat fluxes. So this is just H times AS. And then we have to multiply by a temperature difference that makes this quantity positive whenever stuff is flowing out. And then that would be the temperature of the object, T, minus T infinity. But because this is a heat flux going out, we have to add the minus sign that shows up as a result of the fact that there's a minus sign in the E out expression. So we get negative this. Okay? So I know that it's a little confusing to assign positives or negatives. This is just the way that I prefer to do it. And if you have a better or more concise way of doing it in your head, you should totally do that. Okay? But this is the expression that we wind up obtaining. And this looks like a perfectly nice, solvable, or ordinary differential equation. And it is. But I'm going to do a couple of things, just retooling a couple of variables here to make it even simpler. All right? What I'm going to do is I'm going to say, well, I don't necessarily want to frame this in terms of the temperature per se. What I want to try to do is I want to find the temperature difference of this object between its current temperature and its steady state temperature. So I'm going to define this delta T as being the temperature of the object minus the temperature of the object at steady state. That is to say, as time goes by, what is the eventual temperature that we would expect this object to reach? It's going to be some value TSS, and this TSS we use as kind of a temp pole to define a temperature difference. Okay? If we do this, well, in this particular scenario, what is TSS? Well, it's just T infinity. Because as time goes by, we expect the temperature of the object to reach the temperature of the fluid surrounding it. That's what is eventually going to stop the heat transfer from occurring. And this distinction seems kind of silly because why would we define a new parameter when we already have T infinity if they're just the same thing? At the end of the lecture, you'll see why. But we define this delta T, and the important thing about this is that the derivative of this temperature difference with respect to time, because this is just a constant value, this thing, using the chain rule, is just the same as this thing. And the beauty of this is that it allows us to create an expression for this equation that's even simpler than the one that we already have. And that expression is just the following. So this is just Cp, rho, times the volume, and then the derivative of that temperature difference over time. And then this is equal to minus HAS, and then noting this equivalence, this is just delta T again. And so now we have created a first order ordinary differential equation that we can straightforwardly solve to get what the temperature or the temperature difference between this object and its steady state value is as a function of time. So, skipping the calculus, what you wind up obtaining is that supposing that this object has some initial temperature T0. So at a time equals to 0, the temperature is equal to T0 for the object. If we define it this way, then delta T is just delta T0, which is just, right, T0 minus the temperature of the steady state. This temperature difference multiplied by a negative exponential. And the coefficient in that negative exponential is just this divided by this, right? So minus H T divided by Cp rho times the volume. And so this is an expression, a universal expression, that tells us what the temperature difference between the current temperature of an object and its steady state temperature is as a function of time and as a function of that initial temperature difference. And it doesn't matter if this number is positive or negative, right? Like this delta T0, that initial temperature could be larger or smaller than T infinity. And it's not going to matter. This expression is going to be equally valid. So what information can we glean off of this? Well, notice that this is always a negative exponential. And what that means is that if I were to plot, the absolute value of that temperature difference between the current value and the steady state value, we would find that the temperature difference decreases exponentially, okay? Like it all, and when I say decrease, right, we're talking about the maximum value, or sorry, the absolute value. So it's valid to say that this thing will always decay to zero. But it will decay to zero asymptotically in the sense that it will never actually hit zero because an exponential, a negative exponential, never actually hits zero unless t is, infinity. And so the behavior that we observe is that the heat transfer rate and that the temperature difference is going to go down slowly and slowly and even slower. It's never going to reach that temperature difference, never going to be exactly zero, but it's going to come really, really close. It's going to come arbitrarily close. So that's what we get. The other thing is that it tells us how we can govern, like what are the parameters that affect how quickly that temperature difference is going to change in time. If you think about it, right, this is a constant, this is a constant, this is a constant, this is a constant, and this is a constant. What that means is that we can group all of these together by defining this thing tau, a thermal time constant, okay? And that thermal time constant is going to be Cp rho times the volume divided by HAS. Right, so just the inverse of this. And we can, of course, notice that the volume over the surface area is showing up again, right? And so we don't really have to write the volume and the surface area independently. We can also write this as Cp rho Lc divided by H. And so this little expression here is what is commonly referred to as a thermal time constant. And the larger this value is, the longer it takes for the system to equilibrate, right? The longer it takes for this temperature difference to mellow out. The smaller it is, the quicker it'll equilibrate. And does that make sense? Can we analyze this expression to see whether or not it's true? Sure. If we take a look at this, right? If we make the object larger, if we increase its volume, then it's going to take longer for it to equilibrate. That makes sense, right? If we make the surface area of the object larger, then it's going to take less time for the object to equilibrate. That makes sense too. If we increase the heat transfer coefficient between the object and the environment, it'll take less time. Yep, checks out, right? All of this makes sense. So this tau is this thermal time constant that gives us an estimate of how quickly or how slowly the system decays. And we can write down that expression for the delta T in the following form. Right, where we've now absorbed all of these parameters into this single little thermal time constant tau. Pretty neat. And the behavior is completely consistent with what we had talked about before. No matter what the initial temperature of the object is, eventually it will reach that steady state temperature, which is the temperature of the environment. And so it all works out. And this model is usually referred to, right? This equation and this way of modeling a system whose temperature changes over time is usually called the lumped capacitance model. And the reason that it's called the lumped capacitance model is because this object is behaving almost like a capacitor in a thermal circuit. Right? You can imagine, although we won't stretch this metaphor too much, you can imagine that you can treat this object like some kind of thermal capacitor that's discharging or charging up its thermal energy that is connected to a convective thermal resistance, which is the fluid that surrounds it. And so this is kind of the idea of where this lumped capacitance model comes from, right? Because we're effectively modeling this singular object as a thermal capacitor. Now, there's one mystery that remains, which is why TSS? Why did we even bother with making this connection? And the answer is kind of interesting. Here's another scenario that we can also study. Suppose that we have another object. It's similarly surrounded by environment, which is at, it has some thermal, some heat transfer coefficient H. It has some ambient temperature T infinity. This object has, let's assume that the Biot number is sufficiently small that we can represent its temperature with a single value. It has a single temperature. It has the same material properties that it had before, except that now this thing has a Q dot. Okay, now this object is generating, has a constant rate of thermal energy generation inside of it. So now this seems kind of weird because, well, when we had done the energy balancing for the system, right, we had neglected the Egen term. Now we can't do that. So how do we do it? How do we fix it? Well, let's take a look at the analysis again. Right, this is the energy balance that we did before. This time, this number is not going to be 0. We also have, right, that there's going to be some initial temperature T0. And we can ask ourselves right from the start, what is going to be the steady state value of the temperature of this object? Right, it should reach a steady state value, so what is it going to be? And the answer is that, well, okay, we can use the same energy balance to try to figure it out, because we're looking for the steady state value, so that means that we can get rid of this term and then balance this with this. So what do we get? Skipping a couple of steps, what we wind up getting is that, right, this term is 0. The energy going in, we're just going to assume that this is 0. And so this equation turns into Q dot times the volume being equal to HAS times the temperature of the object minus T infinity, right? So I've done a couple of simplifications. I basically just took this, moved it to the other side, and set this being equal to each other. All right, so that's all I did. And so we have this statement that is only true when this temperature reaches steady state. And so we can solve for the temperature of the steady state system by, plugging in all these values, but we're not actually going to do that. That's not going to be that useful. You'll see that this is going to be very useful for the analysis that we're about to do. So now that we have this expression, now let's analyze it from the perspective where the system is not in a steady state. Okay, so this E dot gen term, which is not 0, is equal to this, but this is also equal to this. If we assume that the heat transfer is happening entirely outwards, then we find that E dot out, right, has to be H times AS times the temperature of the object at whatever time we're analyzing it at, minus T infinity. We assume that nothing is going inside, and this rate of change of the energy of the system is exactly the same as what it was before. Right? So this E sys term is just Cp rho times the volume times the derivative of the temperature with respect through time. And so if we write down the entire equation that we had before, something funny is going to happen. Okay, so Cp rho times the volume, dt over dt. Well, this is equal to minus this quantity. So minus HAS T minus T infinity. And then plus this quantity over here, Ts dot S minus T infinity. Got to make sure I don't go past the limit to the board. These terms have something that cancels, right? Note the negative. This negative multiplies this to generate a positive HAS T infinity term. And this is a negative T infinity term. And so what happens is that the T infinity terms actually cancel out. And so what we're left with, if we try to analyze this, is HAS, the steady state temperature of the object, minus its current temperature. And you can see that if we do the same thing where we just go and say, oh, well, delta T is just equal to the temperature minus the steady state temperature, the equation that we get from this is exactly the same one. Right? We still wind up getting that the rate of change of this temperature difference is equal to minus HAS times that temperature difference. And so the whole reason that I wanted to define this kind of steady state temperature in the first place wasn't to just confuse you, it's to understand that even if I have a different heating or cooling scenario, even if I have an object that has a constant thermal generation rate, we can actually find that the equation and therefore the solution that tells me what its temperature is going to be as a function of time and its, temperature difference relative to its steady state, that is going to be exactly the same. And so it doesn't matter if I'm taking a potato that's not warming itself up and dumping it in a lake of cool water, or if I'm taking the potato that's in the water and then kind of turning some weird thing inside of it that causes it to generate thermal energy at a constant rate. It's not going to matter. The governing equation will be the same as long as that Biot number is smaller than 0.1. Or more precisely, as long as that Biot number is sufficiently small. And so, like we talked about before, this is you commonly call the lumped capacitance model, and it is one of the best tools that we have available to be able to understand how we can see the temperature changes of objects over time. And we've derived this fundamental fact, which is that under the right conditions, that temperature change is going to be exponential, right? That the difference between the temperature of the object and its steady state over time, that temperature difference is going to decay exponentially over time, which is roughly consistent with what we think would occur. So a victory for the approximations and assumptions and then the entire field of study of heat transfer that we've been building up so far. And so now we just have a couple of things that we have to address, not necessarily from the perspective of trying to see how we analyze the behavior of things over time. That's a little too complex. But we do have questions that we have to ask ourselves about, well, what is the behavior of the fluid around it? And how do we find an H? Not just from the perspective of experiments, but also how do we construct the experiment that lets us find what H is? And we'll talk about that in the coming lectures.